Okay, so let me very briefly recap what we did yesterday. Just the most important points. So I briefly introduced the Kerr spacetime. And then we analyzed some of the peculiar properties of Kerr. So for instance, that these zero angular momentum observers pick up a non-trivial azimuthal velocity as they come closer to the black hole due to the rotation in the spacetime. Then we discovered this region called Ergo region, where the asymptotically time-like killing fields become space-like. And due to this property, we then found that, okay, we can generate these particles that have negative energy, and if these particles then accrete onto the black hole, they effectively extract energy from the black hole. And we explicitly studied this in the context of the Penrose process, where we found that we can throw in a particle, let it break up, and then the outgoing energy is bigger than the ingoing energy. Okay? Okay. And then I tried to, or I started introducing the framework that we're going to use to translate these findings, in a particular the Penrose process, from this kind of classical particle picture to a more wave-like picture. And so the way I did this was by introducing the Lagrangian. And the associated equations of motion. And then what we did was, okay, let's start with the nonlinear solution to these perturbative equations that we already know, which is the Kerr spacetime, and perturb it by some small linear perturbation, both in the metric. So it's just the Kerr at 0th order and then some perturbation h alpha beta, plus a linear perturbation to the basically 0th order solution, which is 0 of the Klein-Gordon equation. Okay? And so then we realized that the underlying equations for those two decouple completely. And so we can just study the 2 degrees of freedom completely separately. And so we don't need to worry about, what h does in order to find a solution for phi or vice versa. And so the equation that we're actually interested in is not the equation for h alpha beta, because as I said, around a Kerr black hole, this just kind of corresponds to, or the solutions to the equations for h alpha beta are basically just decaying solutions, which are the quasinode modes, for instance, of a Kerr black hole. So the assumption is that, let's say we have some black hole, and the gravitational perturbations around that black hole are very small, then we can make the assumption that h is basically 0. But also due to the fact that the 2 equations decouple, it kind of makes sense to just study one of them and ignore the other. And so the equation that this capital phi follows is just the Klein-Gordon equation on the Kerr background. And today we're going to try to actually solve this equation in a particular regime that is of biggest relevance to trying to understand how these boson clouds emerge. Okay. So how do we make sense of this? For now, it's just a very complicated second-order partial differential equation that we have basically 0 control over. So kind of the first the first step to trying to make sense of these equations is to just write out what this box operator actually is. So the box operator is basically just what I already wrote on the board yesterday, is this. And so you can then write this out just, basically term by term, writing out the covariant derivatives and then plugging in the components of the metric. Now, this is going to turn quite messy quite quickly. So I'm going to write the very first term, and then I'll let you work out the rest in the tutorial. But I promise that it's actually not that bad. If you keep the metric components as metric components like this for as long as possible and not plug in the Kerr metric, then the equation actually becomes kind of tractable, and it's not like a huge mess that covers the entire page. Okay. Okay, so because I want you to work this out, I'm just going to write out the equation that you're going to find in a schematic form, but in a schematic form that kind of captures the most important details that we're going to be interested in. So I'm going to write this out first, and then I'm going to discuss some of the features. Okay, where these two differential operators are the following. So D, there's capital DR. There's a second order operator, which is and then the polar coordinates are, the operator is, okay, so at first glance, we haven't really gained anything because the equation is substantially longer than what we started out with. But there are a couple of key features in this equation that will help us actually solve this equation in a particular context. And so the first kind of thing that could have anticipated already is that there's no t and no phi dependence in any of the functions. So the functions only depend on r or theta. And that's obvious because, well, the metric has, the time translation symmetry and then the azimuthal symmetry. And so it just doesn't depend on t. And so then there's no way that this t dependence or phi dependence would enter this equation, okay? And then secondly, what we observe is that the r dependence and the theta dependence only occurs in the form of a sum. There's never a product of like, r squared cosine squared theta or something. And this already hints at the way to solve this equation. That's by a separation ansatz. And so to do that, let us let me write down an ansatz for capital Phi that is gonna basically separate this one equation into two equations, where we then have a second order ODE for in just the radial coordinates and a second order ODE in just the polar coordinates. Okay. So the ansatz is kind of the most obvious thing you can write down. So here you're basically just assuming, okay, you have some exponential form of the t and the phi dependence. This kind of makes sense because you want the phi to be an eigenfunction of the second order in time or second order in phi. So basically, you want t squared phi to be proportional to phi, and then similarly for the azimuthal coordinate, and that you can achieve very easily by just having this exponential. And then the second ansatz is, or the second part of the ansatz is that the radial and the polar dependencies come in as a product. Now I should stress that this is only an ansatz, and in fact, as it turns out, if we use this ansatz in this equation here, then we're making some assumptions about the shape and form of the solution. Not all solutions to this equation are of that particular form. So you won't find all the solutions to this equation using this ansatz, and so you'll be missing some solutions. But the solutions that we're interested in are of this form, but it's just useful to keep in mind that not all solutions are of this form. Okay, and I should stress, and I'm going to say this now and probably never again, that phi is a real scalar field. And so technically speaking, this is not the ansatz, but instead, if you add the complex conjugate to it, it's the ansatz. Now, for the most part, I'm going to forget about the complex conjugate because it's a linear equation, and so either of the two will solve the equations. But at some point, maybe tomorrow or the day after tomorrow, it will be important to not think about this as a complex solution, but as a real solution. Okay, let me write this in brackets. Okay, and so what you can already see by looking at this equation is what I kind of already said, is that if you were to plug in this ansatz into this equation, then basically you will get that everything that depends on r is only added to everything that depends on theta. And so that way you can then apply separation of variables. You can introduce a separation constant and then get two equations from this one equation. Okay? Now the details of this you're going to work out, but it's basically the standard approach to solving these equations. Okay, so let me write down just the resulting two equations. So first the polar equation. And then the radial equation. Okay, so here the lambda is the separation constant that I implicitly introduced. Right, and I should probably remind you that this delta is just a function of r and explicitly given by this. And so it only appears in the radial equation. Okay. Okay, so what have we achieved so far? So far, we have been looking at this, or better here, this seemingly intractable equation, second order PDE, and then found that, okay, it doesn't really depend on time and phi explicitly, and even further, the radial and the polar dependencies kind of add up as opposed to multiply. And so that way we were able to make a separation ansatz, or make an ansatz for the scalar field, which then separates this master equation into a second order ODE for the polar dependency and a second order ODE for the radial dependence. So we've already simplified the problem significantly from a PDE to a set of ODEs. Now it basically boils down to solving these equations, and this is a kind of a coupled eigenvalue problem because you have this separation constant lambda, which you don't know, and so you need to impose some boundary conditions, solve the equations to find this eigenvalue as well as the solutions S and R. And in general, you can't do this analytically, and in fact, probably for the regime that we're most interested in, you can't do it analytically. But you can do it in a particular limit, which is still, let's say, marginally interesting. And in what way it is marginally interesting, we'll see. But to solve these equations, let's make another approximation. And this approximation has kind of an intuitive way to understand it. So what we're going to be interested in is the regime where mu times m is much smaller than 1. And this is equivalent to the following. So I can introduce a length, oh, maybe not lambda, maybe lambda tilde. I introduce a length scale lambda tilde, which is basically 1 over mu. And so to understand this lambda tilde, it's basically the Compton wavelength associated with this massive particle of mass mu. So it basically just gives you a length scale, or like basically a length scale associated with the scalar field. I put a twiddle here because the actual numbers aren't too important, but just intuitively you need to understand that it's a length scale associated with this solution, and the length scale is roughly 1 over mu. And so then this this regime is then equivalent to basically where the size of the black hole, so basically the Schwarzschild radius, or m, is much, much smaller than the wavelength of the solution that you're going to look at. Okay? And so intuitively what this means is that you have your black hole at the center, some spin. And then the solution that we're going to find looks something like this. Okay? So the length scale associated with the black hole is basically m. And so if I write it like this is m. Whereas the length scale associated with the solution is lambda tilde. and obviously lambda tilde is much larger than m. Okay? But I should also stress, and this is kind of an intuitive way to see this, that most of the relativistic effects will be completely neglected, because most of the solution actually sits very far away from the black hole, as opposed to close by to the black hole. And so most of the interesting phenomena associated with energy extraction and gravitational wave emission are all suppressed in a particular way in this limit. And we're going to see exactly how it is suppressed and how it gets enhanced as we assume that the two are roughly comparable. Okay? All right. And then I should also say that this kind of implies that the frequency is also much smaller than 1. This you can perhaps see intuitively because the potential for this massive particle at infinity is basically the mass. And so if the mass is bounded like this, then the frequency of any bound state might also be bounded like this, because the frequency is. Okay. But this will become more clear perhaps when we see the solution. All right, so right, and then I should also remind you that again we are interested in the sub-extremal Kerr case, so A is bounded by M. Okay, so basically now the name of the game is to assume this and this and this, of course, and basically look at these equations and remove all the terms that are subleading in an expansion around this limit. And what this implicitly implies is also that you're expanding for in large radii. So basically you're assuming that R is much larger than M. Again, this you can intuitively see because, well, most of the cloud is supported away from the black hole, and so you're mostly interested in distances from the black hole that are much larger than the mass of the black hole. Okay, so taking all of these things and plugging them in here, we can try and understand what happens in this limit. Okay, so let's look first at the polar equation because that's kind of the simplest one. So this is mostly going to be copying because only a single term actually drops out. Okay, so the only thing that actually happened here is that, maybe I should say, mu m much smaller than 1, and A bounded by M. Okay, so these are the assumptions that basically, so this way you can then go from the original equation that we found, basically the Klein-Gordon equation separated with our ansatz, to the simplified equation where the only term that disappeared is this term. And so the reason it disappeared is because A is bounded by M, so at most A can be M, but then of course you have the product M times mu, and you're assuming that to be small, and so in the 0th order case you just set it to 0. Does anyone recognize this equation? Sorry? That's right, associated Legendre polynomials. So the solution to this equation, in combination with this part of our ansatz, is just the spherical harmonics. And the polar part is just the associated Legendre. So S basically goes to ML cosine theta. And that implies that S times e to the I m phi, that's the convention I used, equal to the spherical harmonics. Spherical Okay. What this also implies is that lambda, the eigenvalue, is actually just this, which again follows directly from this. And then this also implies that M is bound this in particular way by quote unquote the value of the eigenvalue. Okay. Now, for the radial equation, we have to do a little more work because there's not just a single term that drops out, and we also need to keep some of the terms which are relevant. So let's try and do this term by term. Okay, so let's look at the first term. So we have a delta, another delta, and then some derivatives. And so the delta goes like this, or is equal to this. And so because this assumption that the wavelength of the solution is much larger than the size of the black hole implied that we're looking at large distances. And so basically here we can just keep the r squared, because this is just a constant. This goes linearly in r, and this goes quadratic in r. So at large distances, the r squared will be most important. Okay. So r squared. Okay, so that's the first term. Okay, what about this term? So here, is also quite simple because A, again, is bounded by M. So at most, A is M. And so then you have omega squared. Oh, no, right. So then you're comparing R to M, but R is much larger than M. And so the only thing you're keeping here is the omega squared R to the 4. Okay, so let's write that down. Okay, so let's see. Let me skip the next two terms and then move to the last term. And then you will see that those two are subdominant. I mean, here you can already see that this a squared m squared will be subdominant, because of course you have a thing that scales as r to the 4 here, and this is a constant, so that's negligible. And same with this thing, it scales linearly in r, and is also suppressed by an n times omega. And so that's also subdominant to this original term. So basically, a squared. Okay. And then this last term is a bit more involved. So let me write this out. This goes to e squared r to the 4. Okay, so why does this happen? So the first term is quite obvious. Here we're just taking the r squared from the delta and then multiply it by mu squared r squared. And then obviously all the other terms there are set down, and if you multiply by this, and so the only term that remains is the mu squared r to the 4. It's the same reason that we only kept the r to the 4 here. Then the second one just drops out entirely because again it's just a constant, and a again is bounded by m, and therefore this is very small. Right, then we don't know the value of lambda, or well, we know that the value of lambda is some constant, but because we have a mu squared here, and we know that mu squared must be much smaller than 1 over m, and r is much larger than 1 over m, we don't really know whether how this compares to that one. Okay, and the same is true here, because we now have a different power in mu and a different power in r. Okay, so we're just going to keep all of those terms. How are we getting the third term? So it's this one times this one. Yeah. Okay. So the first thing to notice, or maybe let me write down the equation that we're going to get from this, and then discuss the equation. So, right. So the equation that we're going to get, and I'm going to write it in a particular form, r squared. So this is the radial equation that we're going to get. In this limit. Does anyone recognize this equation? Schrödinger equation, yes. Assuming which potential? It's a 1 over r potential. And in the hydrogen atom, you also have a 1 over r potential. And it's basically exactly that. Of course, it's not exactly that because you don't have a charge here, but the scaling of the potential is exactly the same. In fact, the equation is identical. You just need to do some redefinitions of what the charge is in the hydrogen atom and what the energy is, but the equation is identical. In fact, we know that the lambda is also, or that the polar, or the angular solution is the spherical harmonics. And so together with the radial solution and the spherical harmonics, the complete solution will just literally be the solution to the hydrogen atom, making some redefinitions of this. Okay. So let me introduce some terminology that people tend to use in this context. Good question, good question. Right. So the reason that happens is the following. So here in the polar equation, the term that dropped out was proportional to a squared. And the a squared is the spin in the black hole spacetime. And the spin breaks the spherical symmetry of Schwarzschild, right? So for zero spin, there is spherical symmetry. And so if you drop this term, you're basically restoring that symmetry. Okay? And then similarly, in the radial equation, the same thing happened. We dropped all the terms that are proportional to the spin, which breaks the spherical symmetry, and therefore we then regain that symmetry as we expand the equation. And in fact, that will not be the case if you consider higher order terms in the expansion in this variable. Because then you'll keep more terms in the spin, and then suddenly the symmetry breaks in a particular way, and that will manifest in the eigenvalue spectrum of the solution. And in fact, I'll mention this in a couple moments probably. Okay. So the definition that people tend to use is that, and then I'm also going to use for the remainder of these lectures, is that this combination mu times m, or equivalently the ratio of the size of the black hole to the wavelength of the solution is defined to be alpha. Okay. So from now on, alpha is this dimensionless ratio. And so then alpha enters in this potential. And basically, the potential then has this form. And because alpha appears here, people tend to call this alpha the gravitational fine structure constant. Because in the case of the hydrogen atom, you would have the fine structure constant there. And you usually call it alpha. And so now we're going to call this the gravitational fine structure constant. Now, I'm going to place this in quotation marks because the terminology that kind of swirls around this subject is very much tied to the fact that these equations do boil down to the hydrogen atom in this particular limit. And so people tend to use terminology like gravitational fine structure constant, bound states, and quantum numbers. But as we'll see, hopefully later today, but probably tomorrow, is that there are very essential differences between the hydrogen atom and this classical system. And these differences will have a big phenomenological impact. And so by trying to kind of force this quantum terminology on the system, you sometimes run into weird situations where you expect an effect to be present because it's present in a, say, hydrogen atom, but it's not present in this particular system. So that's the reason I'm putting this in quotation marks. But this is typically what people call this alpha, the fine structure constant or gravitational fine structure constant. Okay. Right, and then let me define the energy. The energy I'm going to define as omega squared minus mu squared. This is just basically saying that this combination is the energy. And then we can basically import the solutions of this equation that we already know from the hydrogen atom and just relabel some of the things and get the solution that we wanted in the first place for these bound states around the Kerr black holes. Okay, so where am I going to write this? Okay, so the first thing that we're going to get are, we're going to find out what this omega is. So this omega is basically just the Bohr energy levels. Okay, so the energy E omega squared minus mu squared is equal to minus mu squared alpha squared over n squared. So you'll recognize the 1 over n squared is just the Bohr energy levels, and then you have some other constants up top that, in this case, okay, it's this alpha, this gravitational fine structure constant, and then the mu, which is the mass parameter of our scalar field. Okay, and n is quote-unquote the principal quantum number, and it's basically L plus 1 plus what I'm going to call n hat. So n hat just counts the radial nodes of R, so how often it crosses 0. Okay. Then I'm going to define the Bohr radius. So you see the terminology just carries over. The Bohr radius, a Bohr, I'm going to define as 1 over alpha times mu. And this is, again, just in direct comparison to the solution of the hydrogen atom. And so then what we find is that at large distances, this radial solution decays exponentially. This we already know from the hydrogen atom. So let me just quickly reiterate this here. Kr, which for n equals to 1 is just R over Bohr, and K is just mu squared. So at large distances, the radial function and therefore our scalar field configuration, which is just multiplied with R, decays exponentially. And it decays exponentially given by exactly the length scale that is the Bohr radius. Okay? Yeah. Okay. Okay, and then perhaps one thing to note is that omega squared is smaller than mu squared, just because there's a minus sign here. And so basically this implies that we have some bound state. Like asymptotically, the potential is basically mu, and then close to the black hole, it's no longer mu, it's something smaller than mu, and so that allows for the presence of bound states where the frequency is basically below the asymptotic value of the potential. Okay. So basically what this implies is that our solution, capital phi, is really the solution to the hydrogen atom plus the complex conjugate. Okay, so here, maybe I should call this H. Okay, so this is just the solution of the hydrogen atom indexed by the usual indices plus the complex conjugate, because phi is actually a real scalar field. Okay. So let's get some intuition into what this looks like. Okay, so let me just look at one example. And the example is going to be n equals 2, L equals 1, m equals 1, and n hat equals to 0. Okay, and then just, yeah, basically taking the solution of the hydrogen atom, setting all these numbers to be those values, and then redefining, all the fine structure constant in the hydrogen atom by the things that are defined over there. You then find that the solution is the following. So NLM 211 equals to some normalization. For now, I'm not going to worry about what this normalization is. It will be important later. But for now, it's just some normalization. R over the Bohr radius, e to the minus R over 2 times the Bohr radius, sine theta, cos Okay? And so let's look first at the radial dependency. At large distances, okay, it decays exponentially. At small distances, it goes to 0. And so this is basically exactly what I hope I drew here. You have some linear scaling at large radii, and then some exponential tail at large distances. So basically, the cloud is mostly localized at some finite radius away from the black hole, or at least the scalar field is in this particular state. Okay. Then the polar dependence is just sine theta, and basically what this means is that on the spin axis of the black hole, the scalar field vanishes, and so most of the scalar field distribution will actually be within the equatorial plane. Where this solution is not valid. Yes, you're right. In fact, this will be very important in maybe 10, 15 minutes. In fact, I made an implicit assumption that I hope one of you can spot in 10 minutes from now. But most certainly, this solution is only valid in this limit, of course. And on top of that, it's only one particular solution that has the form that we imposed the solution to have. Okay. But yeah, you're right, and I hope in 15 minutes it will clear up what exactly is not quite right here. Right, so the word general is not quite correct, but yes, in principle, you can have a solution because the Klein-Gordon equation is a linear equation, you can just have, a sum of these and it will still be a solution to the Klein-Gordon equation. And so in that sense, you can, generate some state of the scalar field configuration that is a sum of these. But not in general, any scalar field configuration can be written as a sum of this. And the reason is already clear because we already know, I told you that this ansatz won't give you all the solutions. So you can't have that, a sum of these eigenmodes will generate all the solutions of the equation if you already ruled out a subset of these solutions. Right, that's a good question. So the way to understand this is the following. In quantum mechanics, it arose basically on a technical level, by imposing some boundary conditions on the Schrödinger equation, and then the solution happened to have a discrete eigenvalue spectrum. The same thing is true here, okay? But here the interpretation is different. So the interpretation here is that the scalar field will, in the end, kind of describe a macroscopic collection of quote-unquote quantum particles. Because ultimately, we are interested in understanding what an ultralight boson, which is some quantum particle, how it behaves around the Kerr black hole. And the assumption is that this scalar field phi captures this dynamics of these particles in a particular limit. And so basically the limit in which it is captured is the many-body limit at 0 temperature. So basically it's a Boson-Einstein condensate that we're describing by a classical field theory. Perhaps that is a bit too much information, I'm not sure. But basically that's the reason why you have these, let's quote-unquote quantum features in a classical solution. Because you're basically describing a classical system by a wave equation. Right, okay. Right. So let me answer that question in 15 minutes, okay? But it's a good point, it's a good observation. Okay, so, right, so now we know, okay, this, it's peaked some distance away from the black hole. It mostly sits in the equatorial plane. And then we have this time dependence here, which basically just implies that if you looked at the black hole from the top, so the spin kind of goes into the plane or comes out of the board, then the scalar field is kind of like, let's say negative here, it's positive here. Am I doing this right? No, it's the other way. It's not m equals 1. So it's basically negative on one side and positive on the other side. So basically just basically just a cosine. And on top of that, this structure then rotates around the black hole with frequency omega. Okay. Okay, so let me write something down that let me actually keep this. So what I did here was basically consider an expansion in this alpha, and then drop all the terms that are basically subdominant in this expansion. Okay. And then we got this, the Bohr spectrum for our frequencies, and then we found that the solution is this hydrogen atom. But in general, you can of course include more higher order powers in alpha, and as already pointed out, this will basically break the spherical symmetry, and it will introduce higher order corrections to the Bohr spectrum. And so I'm just going to write them down so you have seen them once, because the terminology, again, kind of spills over from quantum mechanics into this, but here it becomes very ambiguous and nebulous what the terminology actually means. So I just want to point out a couple of features. Okay, so what is this frequency, or basically the eigenvalue, more generally? So it's 1 minus alpha squared at 2n squared. This is basically just the Bohr spectrum. And then there are higher order corrections, and the corrections are the following. Of course, it's higher power in alpha, and then it depends on the indices in this particular way. Okay, so basically, this is the Bohr spectrum that we already found. And then all the other terms are higher orders in alpha. And so here is where the terminology, as I said, still carries over but becomes ambiguous. Because now the question is, okay, in the hydrogen atom case, all these extra terms will be the fine structure and the hyperfine structure. But but they arise from physical effects that aren't necessarily present in our system. But nonetheless, people still tend to call these things fine structure and hyperfine structure. And the way the terminology works is the following. So anything that only depends on n is called the Bohr spectrum. Then the stuff that also depends on L is called the fine structure. And then the stuff that also depends on M is then called the hyperfine structure. But of course, this is a bit nebulous because, well, the hyperfine structure in the case of the hydrogen atom emerges from some spin-spin interaction. But here we have a scalar field, so it doesn't even have a spin. And so it doesn't really make a lot of sense to talk about spin-spin interactions. But then on top of that, right, I forgot to define something. This chi that emerges here is just the dimensionless spin of the central black hole. And so perhaps because of the spin dependence, people then call this the hyperfine structure. But you can also see that, yes, at higher orders in alpha, the spin now breaks the symmetry and also the degeneracy in the energy spectrum by appearing at the 5th order in alpha. And in principle, you could go to higher and higher orders in alpha, but it becomes successively more complicated to actually solve the equations. And so people tend to solve the equations numerically for where alpha is basically order 1. Okay, so this is valid wherever alpha is sufficiently small enough. And then when alpha is sort of an order 1 number, then you just have to use numerical techniques. Right, so I raised the equation now, but basically, here we kept everything, just the leading term in the expansion in alpha and R larger than M. But to get these terms, and this is kind of similar to the hydrogen atom, just that the terms look different. In the hydrogen atom, you started out with a non-relativistic momentum, and then the first correction to that was, okay, let's include the first relativistic correction to the momentum. And that is a subleading term. And similarly, you can just, instead of dropping all the subleading terms here, you keep the first subleading term. And if you keep the first subleading term, you'll get this. And then so on and so forth. You just keep higher terms. Which, of course, makes the equations more and more complicated. But yeah. Okay, but so there have been a couple of observations by some of you who noted, okay, well, the boundary conditions aren't quite right, and this hydrogen atom solution seems to have some funny behavior. So is this really the final story? And the answer is no. In fact, we have neglected a very, very important property of a black hole, and that is you can only enter a black hole, and you can never come out. So the boundary conditions at the black hole, or equivalently in the hydrogen atom case, at R equals 0, can't be what we implicitly assumed to be true when we chose to use the hydrogen atom solutions. Because in the case of the hydrogen atom, the boundary condition at the origin is basically that this goes to 0. More generally, this is the regularity condition, but for, I guess, the ground state, this goes to 0. But in general, this is not the case, because in general, we have a black hole there, and a black hole changes the boundary conditions substantially. So in the case of the black hole, Right. So, okay, right. So let me first perhaps illustrate what will happen in this case. So now we have this membrane, well, the black hole horizon, over which we can lose some of the scalar field energy, or conversely also gain some of the scalar field energy. Okay. So in general, the energy is no longer conserved, purely within the scalar field sector. Okay, because we can gain or lose energy to the black hole purely by imposing the boundary conditions that there is some, flux that can go through R equals R plus, basically. Okay, and the way this must be captured, and I just erased it. The way this must be captured in our ansatz, which was this. The way this must be captured is that the time dependence somehow has to change, right? Because if we have some field configuration, this field configuration loses energy or gains energy from the black hole, then somehow the configuration must change over time, okay? But here we wanted this to be an eigenfunction of basically this operator. And so this is kind of the only thing we can write down, okay? But then in order to introduce a different time dependence based on this is basically just to assume that omega is no longer just real, but instead also has an imaginary component. Okay? This is kind of just the presence of this imaginary component is basically an artifact of the fact that the energy is no longer conserved. We can lose energy to the black hole, and then this imaginary part would basically tell us how quickly we are losing energy to the black hole, or vice versa, we can gain energy, and then this will tell us how quickly we'll gain energy. Okay, so if I just plug this into these ansatz there, then our scalar field looks something like this. Okay. So again, we have just this oscillatory piece that just kind of happily oscillates in time harmonically. But then in addition to that, we gain this exponential. There's no I here, and so basically what this implies is that phi decays for omega I smaller than 0, and phi grows for omega I larger than 0. And it doesn't just grow, polynomially, linearly, quadratically. It grows exponentially quickly. Okay? So now the question is, okay, how do we find out what this omega I is? And then conversely, how can we find out whether this solution that we're actually interested in is decaying exponentially or growing exponentially? Okay, so to do this, we would need to basically solve the radial and the polar equations, assuming that omega is now complex. So we can no longer import our hydrogen atom solution because, of course, in the case of the hydrogen atom, the frequency wasn't complex. The energy isn't complex, so the energy must be real. But instead, now we want to drop that assumption, and we're interested in those solutions that have a complex frequency. But because these equations are so complicated, actually making this assumption complexifies actually solving these equations analytically quite substantially. And so I'm mostly going to motivate the way to do this instead of actually doing this explicitly, because it would just cover the whole board twice over. So let me just kind of motivate how this works and defer all the details to the following papers. So if you're really interested in all the details, please have a look at those. this is called Klein-Gordon equation. And rotating fluxes. Okay, this is an old paper, but I think it's actually quite instructive to read. A bit more of a newer version of this you can find in Baumann et al. From 2019. At the archive number 10. Okay, so basically what I'm going to do is kind of in broad strokes explain what Detweiler did back in the 80s to basically find not just the solution to the more complicated problem where omega is a complex number, but also actually find the eigenvalue or the imaginary part of the eigenvalue omega, and therefore tell us exactly which states are decaying, which states are growing, and how quickly they're growing. Okay, so in general, how to do this is to first write down the correct boundary conditions. So at infinity, we're interested in those solutions that decay exponentially. Basically, this is the, at large distances, we already solved the problem, basically, and we know that, okay, the solution that we're interested in decays exponentially. Of course, there's also an exponentially growing solution, but that we just declare to be unphysical and just ignore it. So we want the solution at large distances to decay exponentially. And now at the horizon, so previously we assumed, okay, the radial solution has to be, regular at r equals 0. But r equals 0 doesn't actually exist in the way we framed this problem, but instead r to r plus exists. And that's where we impose our boundary condition. And the boundary condition we impose there is basically this. Right. So this r equals 0, maybe I should erase it because it's only true for one particular state. But it's basically r is regular. So it doesn't blow up at the origin. And that picks out one of the homogeneous solutions, and then the other one is what you're describing. Right, so at the horizon, the boundary condition looks something like this. So what is r plus, r star? R star is the tortoise coordinate. That you probably know from Schwarzschild. In Kerr, the definition of it is slightly different, but the idea is the same. And the idea is basically that r towards minus infinity corresponds to r star to minus infinity corresponds to r equals r plus. And r star to plus infinity corresponds to r to infinity. Okay, so basically, we just move the horizon to minus infinity. But the detail is not too important. What this actually means is that if we combine this with this part of our ansatz, then we know that phi at the horizon will go as e to the I omega t plus r star. And so basically what this is just a plane wave going into the minus r star direction. And the minus r star direction is just crossing the horizon. Okay, so basically the boundary condition here is that we have ingoing radiation on the horizon. Okay, so now we know our boundary conditions. And now the challenge becomes to solve the equations. And this is where I'm going to start to just describe it kind of schematically. So the idea is that we split the domain into two regions. One region we call the far region. And well, as the name suggests, this is far away from the black hole. And the idea is that in the far region, we solve our equation. Now, instead of just looking at a real frequency, we now need to look at a complex frequency. So in general, the solution won't be the hydrogen atom. In general, the solution will be a hypergeometric function, a particular hypergeometric function. Hypergeometric function. But basically, it's just some particular function that has a particular name that you can more or less write down. Okay? And what we know is that there are two of these, right? Because we have a homogeneous solution, a second order ODE that's homogeneous. So we get two linearly independent solutions. And then we just pick the one that has the correct boundary conditions at large distances. Okay? That gives us, let's call it the far field solution. And then the near zone is then equivalently just basically expanding the equations. Instead of now at large distances, so r much larger than m, we now expand it around, so let's say this is r much larger than m, then this corresponds to r larger or roughly equal to r plus. So we're expanding the equation around r plus instead of around r to infinity, basically. Okay? And doing so, you can then get a new equation, which you can then solve. Again, you'll get some, now a different type of hypergeometric function. Let's call it r near. And again, you'll get a set of two of those, and then you just discard one of them that doesn't satisfy the correct boundary conditions at the horizon. Okay? So now we end up with two quote-unquote solutions, but the solutions in different regimes. Okay? One solution is valid in the far zone, but not in the near zone, and one solution is valid in the near zone, but not in the far zone. But we can engineer these equations in such a way that there is an overlap region in which the two are valid. Okay, so let me draw this like this. So r to infinity corresponds to this. R equals r plus corresponds to this. And so the hope is that our near zone solution is valid in some regime up to some distance. And then our far zone solution is again valid, at large distances, but up to some regime that overlaps the regime in which the near zone solution is valid. Okay? So we have this overlap region in which we have two solutions. Okay? But since they're both solutions, and in fact both solutions to the exact same equations, in this overlap region, they should be the same. Okay? And so basically what we now have to do is we have to write both solutions in such a way that we can functionally compare them in this overlap region. Okay? And then by comparing them, we can then get a constraint. Well, we can, let me not call it constraint. We can get, we get an equation that is an implicit equation for the eigenvalue that we're seeking. Okay. So generally, this process goes under the name of matched asymptotic expansion. Matched asymptotic expansion. Okay. So the reason I didn't write any of this out is because the hypergeometric functions, I don't have good intuition for this. I don't think many people have a lot of good intuition for this. But ultimately, it's just a set of solutions to the equations we can write down that follow from the radial equation that I now erased. Okay. And then this matching procedure is basically looking at exactly the functional forms of these two hypergeometric functions, figuring out where this overlap region is, and then matching the two in the overlap. And this matching gives you basically an implicit equation that looks something like this. Let me write it as this. Very trivial. It looks very trivial, but if you look at these references, you'll see it's just a very long expression, and I don't think we gain much intuition from actually writing this out. But ultimately, matching the two then gives you an implicit equation for the frequency omega, but crucially omega, not just omega r. So it gives you an implicit equation for the complex frequencies. Okay. Okay, so what is the solution omega that we're finding from this implicit equation? So the solution, and I'm going to write this here because it kind of makes sense. The solution is basically the real part is exactly this. The real part will still be what we wrote down before. Now I'm just going to add this little subscript r. But now we also gain the imaginary part. Okay? And by the length of this expression, you can then kind of get a feel for all the algebra that is involved with actually doing this matched asymptotic expansion explicitly. So let me just write it out, and then we can discuss what it means. Okay, looks good. Okay. All right, so this is the expression, and let's try and understand all the different terms, because of course it's very long and there's lots going on. So let's first understand the very basic property of this equation, that is this larger than 0 or is it smaller than 0? Okay? So looking at this term here, this is strictly positive. And the reason for that is, well, our plus is positive, and then these numbers are all positive. Then this, of course, is a square of something. This is positive. And here, since we're in a sub-extremal case, again, this must be strictly positive. And then again, this is something that is a square, so this is positive. Okay? So everything starting from here up to the end is positive or 0. And then, of course, alpha is just some small number, but it's still positive. And so then we can see that really the only term that matters is the sign up front plus this combination. Okay? And so from this, we can read off the following. The superradiance condition. Superradiance condition. And this condition is that make a box around it because it's very important. So the superradiance condition is the condition under which omega I is positive. Okay, so whenever the real part of the frequency satisfies the superradiance condition, then we can see that, well, this becomes negative, there's a minus sign up front, hence omega I becomes positive, and therefore phi starts growing exponentially. Okay? So basically now we know that we have learned that under some conditions, and that is the superradiance condition, on the solution that we're actually after, if the solution satisfies this superradiance condition, then we know that our field grows exponentially. I'm just copying this, but maybe I should give this a name. So where it grows exponentially, this is an instability because now the field configuration that we start with over some time will have gained amplitude, basically. And it gained amplitude exponentially quickly. And so this is an unstable process, and this is called the superradiance instability. Superradiance instability. Okay. Now this doesn't always happen, because of course not all the field configurations in general will satisfy the superradiance condition, and therefore will grow exponentially. And if they don't, then this is necessarily true, that they all decay exponentially, at least in a subset of the solutions that we looked at. But there is some subset of solutions which do grow exponentially. And ultimately, this is the reason why I said that yesterday, that the solution phi equals 0 is not a good solution. Because if we have growing modes in the solution space, then any tiny perturbation to this, that it will have some non-zero overlap with the unstable modes, will necessarily over time develop some value that's very much non-zero. So it's very far away from 0, and therefore it diverges away from the solution you started with exponentially quickly. Okay. Maybe let's call it here. Are there any questions? Mm-hmm.
So that will affect the growth of this scalar field, is it?
Right. So ultimately, right. So ultimately, the process, because I was saying the energy is not conserved, the process in which, or the field configurations which have positive omega I, they will extract energy from the black hole, and ultimately that's a finite source of energy. Okay. So once that energy is all extracted in a particular way, and we'll find out exactly how that happens, then the exponential growth will stop. But I'll explain tomorrow, basically, how this happens and why it happens.
Thanks. The three approximations that you used to simplify the equation. I mean, so one was that A is approximately equal to M. So this expression is valid only for extremal configurations.
Sorry, no. So the one approximation I did was I just assumed I can leave out the twiddle here. The reason I put the twiddle there is that A can be, M minus epsilon, where epsilon is a tiny number. And so it can go up to M. It's basically bounded by M. And so that then was relevant for some of the expressions that I wrote down. But ultimately, this effect is obviously largest if the spin is largest, because then we have the most energy, rotational energy in the black hole to play with. And so that's the most interesting regime.
I mean, this is anyway true for black holes in TR, right?
Well, yeah. For black holes that we believe to be astrophysically relevant, that is true, yeah.
Any other questions?
Standing gravitational waves. So by standing, you mean what exactly? Right. So the cloud itself can be interpreted as a standing wave, because at large distances, the boundary conditions for this is basically 0. And so then, yeah, the only thing that happens is that this field configuration rotates. But in that sense, it's a standing wave. The gravitational waves, on the other hand, no, because the boundary conditions for the gravitational waves at infinity are outgoing. And so basically, you can just, the wave that goes out is just, it just never gets reflected. And so you can't generate a standing wave. I see what you're saying. No, and I'll explain on Thursday exactly why that is not the case. Basically, yes.
So there would in general be another part which would not satisfy the exponential boundary condition of infinity, but the quasi-normal behavior. Where waves are exiting the...
Right. So you're talking about the scalar fields?
Yes.
Right. So scalar field perturbation with frequency omega larger than mu, they can escape to infinity. And for those, the boundary conditions would be outgoing radiation. But because it's a massive field, it always has to overcome this mass barrier. And so for gravitational waves, this will always be the case because there's no mass. But, yeah.
And can there be a special situation where the exponential growth of the scalar field could trigger a collapse?
A collapse of the cloud?
Whole system.
Well, I mean,
Additional black hole.
an additional black hole. So the word collapse triggered a thought, and I can maybe share this thought. So people have been thinking about this Boson-Nova process. This would be triggered through self-interactions of the scalar field, so it wouldn't just purely be the Klein-Gordon equation, but Klein-Gordon equation plus 5⁴ corrections, let's say. Now, I think the consensus is that this won't actually happen, but even if it did happen, I would highly doubt that it does actually create black holes, because I don't see a process through which you can then concentrate sufficient amount of energy in small amount of space to collapse to a black hole. That is not the Kerr black hole you already started with. Right? So yeah, I'm not sure.
I think there was a question at the back. I saw a hand raised.
Right, good point. No, so the alpha doesn't change, but the alpha is not really a fine structure constant in the sense it is in QED, let's say. Like the fine structure constant has a definite number and it doesn't change, right? Or, well, we believe it doesn't change. Here, this is not the case, right? So alpha here is mu times m, right? And m is the black hole mass. And we have black holes of different masses. And so for a fixed mu, the alpha will be different for different black holes, okay? And the assumption is that this mu is the mass of the boson, and presumably the mass of the boson is the same everywhere in the universe. And so the scalar field will see black holes of different mass, and for each of those black holes, the alpha will be different. And then within if you just look at a single black hole, for which you start with some fixed value for alpha, then this value is practically speaking fixed, but because you're extracting energy from the black hole, the mass will also change ultimately. And so there's a slight ambiguity in which way you define this alpha then, but generally speaking, for a given isolated black hole system and given mass, you assume this mu to be just a parameter of your model that is fixed, then alpha won't change.
So when we took omega r to be a real quantity and we got that expression, and when we imposed the correct boundary conditions of ingoing waves, we still got the frequency to be the same. So like physically, how do we see that still holds, that is still correct?
Right. So the way intuitively to think about this is, and you can't really see it from, well, you can kind of see it from the expressions, but not really. So if you look at this hard enough, what you'll see is that the real part of the frequency is much larger than the imaginary part of the frequency. So basically what happens is it just oscillates much more quickly around the black hole than it grows in time, okay? And so in making the assumption that where we ignore the imaginary part completely is basically in expansion in time scales much faster than omega I, or 1 over omega I, okay? And so there, in that sense, you can neglect this because this is a subleading term.
So maybe we can take one last question.
Since the omegas are quantized, so the system can either lose energy in quantas only. So if it loses energy in form of gravitational waves, so will it be like in quantas, or in what way will it be?
So the extraction of the energy, so this is an entirely classical process, and the quantization that occurs here is again just a purely classical quantization. The underlying assumption, and this is kind of what I was hiding here in the normalization, which we haven't discussed yet, is that this normalization will basically tell you that the entire cloud of bosons contains a macroscopic amount of energy, meaning like a few % of the mass of the black hole. And so that can't be carried by a single particle, right? Because a single particle, and again, this I haven't told you, but the single particle has a mass of like, 10 to the minus 10 eV or something, which is very much not a solar mass black hole, right? And so basically what happens is that a very large number of bosons sit in this state. And so then you can describe this state as a classical field configuration as opposed to some quantum process. And so this classical field configuration has this quote-unquote quantization relation where the frequencies are discrete, but it doesn't mean anything for the individual particle. It just means that the macroscopic number of particles then generate a classical field that looks like this. Okay, and so the gravitational wave emission will again be a classical process. So you can imagine, okay, you have this kind of dipole-like shape here, and so then in the stress energy tensor that sources the gravitational waves, you'll have a square of the scalar field, so you get some kind of quadrupolar pattern. And this rotates around the black hole, and therefore the quadrupole will then emit gravitational waves. And this is a purely classical process. There's no like, it emits one graviton at a time. It's a macroscopic number of gravitons, if you want.
And what is the time scale of like a decay and growth? Like what is like omega I, order of magnitude kind of?
Right, this we will discuss tomorrow, but it depends. It can be like from, let's say, a few, months for a scalar field up to any large number. But I'll describe this in more detail tomorrow.
So in interest of time, let's continue this discussion over lunch and thank Nils.